I think that might be yours. This is definitely mine.
Yeah, that's mine. Okay.
Quick little PSA, our speakers are not harmful. They do not bite. If you would like to take a seat over there, I think we should be good. Sure. Cool. Welcome, everyone, to this edition of New York City Systems. I'm Angelo, and our co-hosts, Phil and Aaron, are here. So thank you so much for joining us and all their hard work and effort to bring the speakers and spend your presence through this rain. It's kind of quite interesting. Without further ado, our first speaker, Manya Bansal. She will present Prism, a new GPU programming language designed to restore modularity without sacrificing low-level control over collective operations in her topic. Modular GPU programming with type perspectives. Everyone give it up for Manya.
So I just use this, right?
Yeah, you're good, yeah.
Okay.
No, this is for the crowd and that's for the recording. So,
oh, I see. Okay, got it. Okay, awesome. For posterity's sake, it was raining quite heavily, and I would like this to be recorded in this current moment. But let me get started with my actual presentation. So today, I want to talk to you about modular programming for GPUs. But first, I want to talk about why I think the GPU programming paradigm is not modular in the first place. So as a show of hands, how many of you have programmed GPUs before? Okay, awesome. So like 40% of people. So first, let's just do a really quick refresher on GPUs. So on a GPU, execution happens thousands of threads at a time. It's a massively parallel architecture. And the way you program this machine often is through CUDA. In CUDA, the mental model that NVIDIA wants to sell to you is that you're going to be controlling this machine by controlling the behavior of a single thread. So what does this mean concretely? This means if I wanted to multiply two matrices, A and B, and compute the output into C, then I would have to figure out a way to distribute that work over all my threads. And the way I would do it is I can compute the ID of my thread using some of these hardware variables that I have up on the screen. But basically, the upshot is that the value of X is going to be different across all these threads. Now, the remainder of the implementation looks kind of similar to like your normal parallel for loop paradigm, where you can just sort of distribute some computation over some outputs of your actual C matrix. And then all is well and good. You can just write your naive matrix multiply loop. So this is fine. But across these thousands of threads, there's actually a hierarchy within them. So there's a single thread, which is the smallest unit of sequential control. There is a warp, which is a group of 32 threads. Instructions are issued 32 threads at a time. So these threads execute in lockstep. The analogy maybe is that a warp is a single CPU core, and then a thread inside that warp is like a vector lane, if you're used to that kind of programming. Now, there's also a block, which is made up of several warps. And finally, the grid, which is the entire computation that we have, which is made up of several blocks. And this hierarchy is useful not only to organize your computation, but rather also it has intrinsic meaning. So certain operations are only meaningful when executed at that part of the hierarchy. So if we consider the Ampere generation of GPU, the Tensor Core operation, or what is really just a big matrix multiplication, is only valid if a warp's worth of threads or 32 number of threads execute that particular operation. On a Hopper, this is a little bit coarser grained. On a Blackwell, it gets even more coarser grained, but the upshot is the same. Certain operations are only valid at certain parts of the hierarchy. So how do we actually use this Tensor Core operation? This is actually where the majority of our compute lives, so let's actually get comfortable using this. So again, I'm going to start out with a simple matrix multiplication. We're going to use the same technique where we're going to sort of locate ourselves in the entire computation by figuring out our thread ID, different across all threads. And then now we have to make sure only 32 threads actually execute this piece of code. So I'm going to guard it with that if statement. Then the only thing I need to do is set up my inputs, execute the Tensor Core operation, read from the outputs, and then make sure all of my threads are actually done executing this. So I need to make sure I synchronize all of my threads. And if I had made a minor mistake here, instead of 32, I'd put down 31, well, then the Tensor Core instruction would have been undefined, or worse still, can deadlock. And the sync warp would have deadlocked our machine. It's going to wait for 32 threads to get there. That's never going to happen. That if statement doesn't allow that. And actually, this situation is still kind of OK. At least that if statement is inside that function. But if I had to invoke this function in an outer context, which was guarded by an if statement like this, well, now I have to start being really careful. I have to read into the actual implementation to figure out what's happening. So in CUDA, all is kind of well and good when you want to control the machine behavior from the perspective of a single thread. But then all hell breaks loose when threads actually need to collaborate to perform these collective operations. And right now I showed you two implementations, right? Like a warp-based matrix multiplication and our first naive grid-based matrix multiplication. And in CUDA, actually, you cannot tell which one is which, even though they need to be used differently. And one can even deadlock your machine if not used properly. So I'd like to argue that modularity as it is broken in CUDA. And the fact that the ecosystem itself reflects this lack of modularity. So the ecosystem is already built of a lot of what we call like global kernels. So kernels that control the entire machine at once. So these things can't be composed with anything anyway. They just like hijack your machine. And if there is a library which actually exposes sort of like fine-grained control, like the scub library, so it's saying, hey, I'm going to control the warp, thread, or block level part of the hierarchy, well, then the way that you tell the programmer this is what you're doing is you tell them through names. And names can't be checked nor enforced either from the implementer side or from the user, the person who's using it. So you better make sure that you actually understand the documentation. And at this point, you might be wondering, hey, Manya, I've heard about like a bajillion new GPU languages. Like, what about any of these? Do they solve modularity? And so let's take one of these as an example. So I actually want to consider Triton. And so in Cub, the library that I'd shown before, we had three options, so we could get confused. In Triton, we only have one option, so we cannot get confused. Triton does not allow you to control other parts of the hierarchy that are not the block level of the hierarchy. And in some sense, this kind of solves the modularity problem, at least a little bit. But the issue arises the moment you want to control something that's lower from that part of the hierarchy. So on the Hopper, you had these like big coarser-grained Tensor Core instructions that got introduced. And like this is really where all of your compute lives. So you want to get really precise control over them. Triton cannot expose that control to you because it abstracts over it. And this becomes an issue. In fact, to the point that Triton decides, hey, we should like introduce like a lower level interface now. People need to control this thing. And lo and behold, you're back in the same sort of situation. And I think in general, when we look at a lot of these new languages, they either do not address the concept of modularity at all, or try to address it by basically restricting the user to programming a certain part of the hierarchy. And they say, well, if everything lives at that hierarchy, then like, okay, you get composition. And as I'm proposing my language, I'm sure you can tell this is what's going to happen. You might be wondering, well, like what level of the hierarchy do you want to pick? Maybe I want to argue that's the best performant level of the hierarchy. And I think this is like totally the wrong question to ask. I think we instead need to ask, how do we give access to the lowest level interfaces on this machine without sacrificing modularity? Is there a way to allow the programmer to go up and down this hierarchy without like making them go in this like modularity hell? So I would like to argue yes, and I want to introduce a new language that I've been working on. Actually, Joe and Daniel also in the audience around, they've been working on this with me. But it's a language called Prism. It's a low-level GPU language, and it tracks in its type system how a program is using hardware resources. So because we know what resources are being used, we can check at compile time whether those resources are going to be available when a function gets invoked. And the core idea at the heart of Prism is the idea of a perspective. In essence, it is the view of the hierarchy from which any statement controls the machine. So what does this mean? If we go back to our previous example, then the first statement is a thread level statement. X even has different values per thread. The if statement is a warp level statement. Effectively, you are sort of like getting a warp's worth of threads together. The inputs, again, thread level statements, different values per thread. Tensor Core is obviously a warp level statement. It doesn't even make sense at any other perspective. Same for the write to output, thread level. And then sync warp, also a warp level statement. So you can already see how these perspectives are visible even within CUDA. But with this sort of informal understanding, we can start to operationalize our definition of a perspective. So a perspective is really just a level, a grid, block, or thread coupled with a static constant. For those who've interacted with the machine, I've sort of like skipped over the fact that there's some like alignment guarantees that are sort of necessary for like a warp to actually like be a warp. And so by default, you should assume all perspectives are aligned, but I'm not going to go into that complexity right now. So an example of this is thread 1 perspective is a perspective that contains a single thread. Thread 2 perspective is a perspective that contains 32 thread. And because everything is aligned, this is a warp. And then grid is a single grid. OK, so now we can do the same thing really quickly for the same program, where we have the first statement living at thread 1 perspective, the next at thread 32. Same goes for inputs, thread 32 for the Tensor Core, thread 1 for the write to outputs, and then thread 32 for the sync warp. But the question is still, well, we have these perspectives now, but how would Prism actually ensure that these perspectives are respected in the program and we don't actually violate them? And basically, the thing that we do is that we literally expose them in the program source. So as a programmer, you are expected to define and program against these perspectives. So let's see what this program would actually look like in Prism. The first thing we want to tackle is this if statement. Well, how do we actually like shard these compute resources together? And the first construct I want to introduce is the construct of a split. A split says I'm going to shard off some number of threads to execute one branch and another to execute another branch. So this is parallel composition. Prism is embedded in Python, which is why this looks like a case switch sort of syntax, but not to be confused with the fact that these like arms are really executing in parallel. So it's not sort of your traditional case switch semantics. And this is not the only way you might want to shard your compute resources. You might also want to do something called like grouping, where you basically replicate a piece of code over sort of the same sized perspectives. So in this case, we're saying every group of 32 threads is going to be executing this piece of code. So these are the sort of the two ways that we can actually control the compute resources flowing through our program. Now Now group and split actually try to make a promise to the programmer. They say, well, within their scope, there's going to be at least these number of resources available. And actually, even in the way that I've written this program, I can really quickly violate this. So if I take this x variable, which has different values, and I just go and put in this if statement, well, now I'm like screwed again. It doesn't matter if it's in the scope of that group. I actually cannot guarantee the things that I'd like to say. And again, this Tensor Core becomes undefined. And the key sort of issue is that divergence on data can be used to induce divergence on compute. So we try to make this divergence of compute somewhat structured, but you can similarly use data to do it. And the way that we actually handle this fact is that similar to the code, where we actually track the perspective on which it lives, we also track the perspective of data. So let me actually define what this means a little bit better. So if we go back to our program, now, that variable x is actually sort of going to be defined as living at thread 1 perspectives, which is to say it can change the frequency of a single thread. So it can have different values per thread. Now, if you were to try to use a thread 1 variable inside a thread 32 scope, well, then now this is simply a compile time error. You cannot read that variable from thread 32 scope because that variable is changing at a higher frequency than that code's scope. So let's actually dig into these rules, because I think this is worthwhile understanding. So imagine I have one variable, changes at thread 1 perspective, so at the frequency of thread 1, another at thread 2 frequency. So now every two couple threads need to have the same value for that variable. Well, then is it okay if I just like write the value of y into x? Actually, this is totally fine. I'm still meeting my thread 1 contract. Thread 1 just says that the variable is allowed to change at most at that frequency. I'm just changing at a smaller frequency now, so this is still okay. And then if I try to actually do the opposite, so let's reset x, and then let's try to write the value of x into y. So this is going to be actually wrong, and Prism is going to complain about this because you violated y's contract. Now y is changing at the frequency of a single thread, which is not actually how you've declared it. So with that, we can actually now start converting the data in our program into sort of this like data perspective format. So x gets into thread 1. We do the same for registers, and we also now rewrite the actual like function header in this form, so we can take each of the argument of the function header and write it as such. this really means that the value of that pointer is like the same across all 32 threads. So that's what that means there. And then because you can just read from data that lives at a broader perspective than you, this write is totally fine. You can write a thread 32 value into a thread 1 variable. But I get sort of a little bit stuck here now, because I somehow have to write a thread 1 value into a thread 32 variable, and I have to figure this out to actually do anything meaningful. I have to write my actual value into memory. And the way that we do that is that we allow programmers to basically lower the perspective of their data for some well-defined scope. So the way that we do it is we have a construct called partition, where it takes in a piece of memory, it takes in the perspective you want to lower it to, and it takes in a function that we'll apply each time we access that piece of memory. And we also have a new name that we'll use. So if I were to now rewrite this code, I can only use cthread within that scope. My previous name, cmem, I'm not allowed to touch anymore within that scope. And then each time I access cthread, it's just literally the original memory with that transformation applied to it. After the partition scope is done, we're going to synchronize so that everybody sort of agrees on the same state of cmem. And then outside the partition scope, you can no longer refer to cthread. So that's just, again, going to be a compile time error. You're back to cmem being at the perspective we started out with. So with that done, we kind of have to now deal with these last two intrinsics that we were using. And these are like really, this is really the reason why we've been getting here all along. So let's see how we can actually handle this. So basically, every function in Prism comes with this requires thing attached to it. So it says this function is going to attempt to use at least these many resources. The function implementation inside is checked against this. So it doesn't like pass type checking if we actually don't meet this requirement. And then these two different functions simply become function calls. Because now the Tensor Core intrinsic can literally just say, hey, I require 32 threads. And then at compile time, we can just check the fact that it's only called in scopes where that requirement is actually met. So now we can actually just not even need to look into the implementation and just use that requires to do a lot of work for us. So I talked about Prism. I also want to talk about Bundle a little bit. So we formalized a lot of the core properties of Prism that I've been talking about in this core calculus called Bundle. And this is really to just like intimidate people. Horizontal lines are really scary. I support you. But basically, Bundle says that programmers can never execute operations in settings where they don't have the correct perspective. So we sort of have a soundness theorem, which helps us prove certain properties about Prism. And finally, the thing that we actually care about, can we use Prism to write speed of light programs on the GPU? So the first one that we tried was actually we tried to re-implement the single pass prefix scan program. And the reason why I picked this program in particular is because it's not your normal dense linear algebra program. It has very different convergence properties. Again, like intimidation tactic by putting a complicated figure on there. But at the upshot, it requires different kinds of convergence. And we were able to match the speed of light implementation that NVIDIA has put out. So that was a good sign. And then also we tried to implement like the quintessential matrix multiplication on a hopper. So this one required us to use asynchrony on the GPU with both like this DMA engine that the GPU has, these Tensor Core operations. It required us to pipeline a bunch of stuff. It required us to use warp specialization. So really sort of like was an acid test for this language. And we got within 10% of NVIDIA performance. The remaining 10% of that performance actually comes because NVIDIA's compilers optimization pass does not trigger on like Prism code because it's written in like a particular way. So if that optimization pass triggers, it will just sort of work. Otherwise, it wouldn't. So we have to like convince compilers of certain properties. If you're interested in why the code looks the way it does, I can also go a little bit deeper into that, but just ask me a question about this. Yeah, with that, I just wanted to introduce you guys to Prism, and I'm open to any questions. Yeah.